Right now, at this very moment, you are surrounded by something invisible. Something you cannot touch, cannot taste, cannot smell, and cannot hear. But it is everywhere. It is between your fingers. It is between the atoms of your body. It is between the earth and the moon. It is between the stars. It stretches from one end of the universe to the other. And we call it space. Empty space. The void. The nothingness between things. But what if I told you that this nothingness is actually a something? What if the emptiness around you is not empty at all? What if space, the very fabric in which you exist, in which everything exists, has a structure, a texture, a hidden architecture so incredibly tiny that no microscope, no telescope, no machine humanity has ever built can see it? What if space itself is made of tiny loops? This is not science fiction. This is not a wild guess. This is the conclusion of one of the most mathematically rigorous, deeply researched, and intellectually stunning theories in modern physics. It is called loop quantum gravity, and today we are going to go on a journey into this theory. A deep, long, patient journey. We are going to start from the very beginning, from the crisis that forced physicists to even consider such a radical idea. We are going to trace the history of the brilliant minds who built this theory piece by piece over decades. We are going to understand what these tiny loops actually are, how they work, what they predict, and why they might change everything we think we know about reality. Along the way, we are going to encounter some of the most mind-bending ideas in all of science. We are going to discover that area and volume, the basic properties of space, come in tiny indivisible chunks, just like energy comes in chunks in quantum mechanics. We are going to learn that the Big Bang might not have been the beginning of the universe at all, but rather a big bounce, a cosmic rebound from a previous universe that collapsed before ours expanded. We are going to explore what really happens inside a black hole and why the terrifying singularity that general relativity predicts might not actually exist. We are going to see how this theory compares with its biggest rival, string theory, and why the competition between these two approaches is one of the most important intellectual battles of our time. And by the end, I promise you this: the way you look at the empty space around you will never be the same again. So if you are someone who loves understanding the universe at its deepest level, subscribe right now and hit that bell icon, because this is going to be unlike any video you have watched before. Drop a comment below telling me what you think space is made of, smooth and continuous, or tiny and grainy. I want to know your instinct before we dive in. And if you enjoy this journey, smash that like button, because it helps this video reach more curious minds who deserve to know the truth about reality. Let us begin. Before we can understand why anyone would think space is made of tiny loops, we first need to understand the crisis. The deep, fundamental, unresolved crisis at the heart of modern physics. Because loop quantum gravity was not invented out of boredom or curiosity alone. It was invented out of desperation. It was invented because two of the greatest theories in the history of science, two theories that are each spectacularly successful in their own domain, absolutely refuse to work together. And this refusal is not a minor inconvenience. It is a catastrophe. It means that our understanding of nature is fundamentally incomplete. It means that at the deepest level, we do not understand how reality works. The two theories I am talking about are general relativity and quantum mechanics. Let me tell you about each one. General Relativity was published by Albert Einstein in 1915, and it is, without exaggeration, one of the most beautiful intellectual achievements in human history. Before Einstein, gravity was understood through the work of Isaac Newton. Newton said that gravity is a force, a mysterious pull that acts between any two objects with mass. The Earth pulls the apple, the sun pulls the Earth. Simple, powerful, and it worked beautifully for over 200 years. But Einstein saw deeper. He realized that gravity is not a force at all. Gravity is geometry. Gravity is the curvature of space-time itself. What does that mean? Imagine a large rubber sheet stretched out flat. Now, place a heavy bowling ball in the center. The sheet bends, curves, sags around the ball. Now roll a marble across the sheet. The marble does not travel in a straight line. It curves toward the bowling ball, following the dip in the sheet. To someone who cannot see the sheet, it looks like the bowling ball is pulling the marble toward it with some invisible force. But that is an illusion. The marble is simply following the curved geometry of the surface. This is exactly what Einstein said happens in the universe. Massive objects like the sun, the earth, and stars do not pull things toward them with a force. Instead, they warp the fabric of space-time around them, and other objects, planets, moons, even light itself, follow the curves in that fabric. What we perceive as the force of gravity is actually the curvature of space-time. This was not just a philosophical reinterpretation. Einstein's theory made specific, testable predictions that were dramatically different from Newton's. It predicted that light should bend as it passes near a massive object, because the light is following the curved space-time. This was confirmed in 1919 during a solar eclipse, when astronomers observed that starlight was indeed deflected by the sun. It made Einstein world famous overnight. General relativity predicted the existence of gravitational waves, ripples in the fabric of space-time produced by accelerating massive objects, like two black holes spiraling into each other. In 2015, the LIGO experiment detected gravitational waves for the first time, 100 years after Einstein predicted them. It was one of the greatest experimental achievements in physics history. General relativity predicted the existence of black holes, regions where space-time is so extremely curved that nothing, not even light, can escape. For decades, many physicists thought black holes were just mathematical curiosities, not real objects. But in 2019, the Event Horizon Telescope collaboration produced the first image of a black hole in the galaxy M87. It looked exactly like general relativity predicted. General relativity even affects your daily life in ways you might not realize. The Global Positioning System, GPS, the technology that tells your phone exactly where you are on Earth, depends on general relativity. The satellites that make GPS work are in orbit high above the Earth, where gravity is slightly weaker. According to general relativity, clocks in weaker gravity tick slightly faster than clocks in stronger gravity. If GPS did not account for this relativistic time difference, your position would drift by about 10 kilometers every day. The engineers who designed GPS had to include Einstein's corrections, or the whole system would be useless. So general relativity is not some abstract, irrelevant theory. It is battle-tested, experimentally confirmed to extraordinary precision, and woven into the technology of modern civilization. It describes gravity, space-time, the large-scale structure of the universe, and the behavior of the most extreme objects in the cosmos with breathtaking accuracy. But there is something crucial to understand about general relativity. In Einstein's theory, space-time is smooth, continuous. It can bend, stretch, ripple, and warp, but it has no graininess, no pixels, no smallest unit. You can zoom in on space-time forever, and it remains smooth at every scale. It is like a perfectly elastic sheet that can be divided into smaller and smaller pieces without limit. Now let me tell you about the other pillar of modern physics: quantum mechanics. Quantum mechanics was developed in the 1920s and 1930s by a collection of brilliant physicists, including Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, and many others. While general relativity describes the very large, the planets, stars, galaxies, and the universe as a whole, quantum mechanics describes the very small, atoms, electrons, photons, and the fundamental particles that make up all matter and radiation. And quantum mechanics revealed something shocking. At the smallest scales, nature is not smooth and continuous. It is grainy. It is quantized. It comes in discrete, indivisible chunks. Let me explain what that means. Before quantum mechanics, physicists assumed that energy, like space in general relativity, was continuous. An electron orbiting an atom could have any energy it wanted, just like a car can drive at any speed. But experiments showed something completely different. Electrons in atoms can only exist in specific energy levels, like rungs on a ladder. An electron can be on the first rung or the second rung, but it cannot be between rungs. It jumps from one level to another instantaneously, with no intermediate states. This is the famous quantum leap. Light, which we experience as a smooth wave, actually comes in tiny packets called photons. You cannot have half a photon. You cannot have a third of a photon. You either have one photon or you do not. Energy is delivered in these minimum, indivisible units, these quanta. This is where the name quantum mechanics comes from. Then there is the uncertainty principle, discovered by Werner Heisenberg. It says that you cannot know both the exact position and the exact momentum of a particle at the same time. The more precisely you measure one, the less precisely you can know the other. This is not a limitation of our instruments. It is a fundamental property of nature itself. At the quantum scale, reality is inherently fuzzy, probabilistic, uncertain. Quantum mechanics also revealed the bizarre phenomenon of superposition. Before you measure a quantum particle, it does not have a definite state. An electron can be spinning clockwise and counterclockwise at the same time. A photon can be in two places at once. It is only when you look, when you make a measurement, that the particle chooses a definite state. Before measurement, all possibilities coexist simultaneously. And there is entanglement. Two quantum particles can become so deeply correlated that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he hated it. But experiment after experiment has confirmed that entanglement is real. It is one of the most thoroughly verified phenomena in all of physics. Now, just like general relativity, quantum mechanics is not just an abstract theory. It is the foundation of virtually all modern technology. Semiconductors, the tiny chips that power every computer and smartphone on Earth, work because of quantum mechanics. Lasers, which are used in everything from barcode scanners to fiber optic communication to eye surgery, are quantum mechanical devices. Mirror machines, which doctors use to see inside your body without surgery, rely on quantum properties of atomic nuclei. Nuclear energy and nuclear weapons are both consequences of quantum mechanical processes. LED lights, solar panels, atomic clocks, the list is enormous. Quantum mechanics is arguably the most practically successful theory in the history of science. So we have two theories: general relativity, which describes gravity, and the large-scale structure of space-time with extraordinary accuracy, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales with equally extraordinary accuracy. Both are confirmed by mountains of experimental evidence. Both are essential to our understanding of the universe. Both are essential to modern technology, and they are fundamentally incompatible. This is the crisis. This is the deep, unresolved problem that has haunted physics for nearly a century. Let me explain why they are incompatible. In quantum mechanics, and in its more advanced version called quantum field theory, we describe the behavior of particles and fields on a fixed background space-time. The space-time is the stage, and the quantum fields are the actors performing on that stage. The stage does not change, it just sits there, providing the arena in which the quantum drama unfolds. This is called being background dependent. The theory depends on having a fixed background, but in general relativity, space-time is not a fixed stage, it is dynamic. It bends, curves, and responds to the matter and energy within it. Space-time is not the stage, space-time is one of the actors. It is part of the show. This is called being background independent. The geometry of space-time is not given in advance, it is determined by the equations of the theory. So here is the conflict. Quantum mechanics needs a fixed stage to perform its calculations. General relativity says there is no fixed stage. The stage itself is a dynamic, evolving entity. How do you write quantum equations for a field that is the background on which you normally write quantum equations? It is like trying to build a house while the ground beneath you is constantly shifting. But the problem goes even deeper than this conceptual clash. When physicists actually tried to quantize gravity, to treat the gravitational field using the standard techniques of quantum field theory, the mathematics exploded. Literally, the calculations produced infinities, not just large numbers, but infinite answers for physical quantities that should be finite. Now, this problem of infinities also appeared in other quantum field theories. In quantum electrodynamics, the quantum theory of the electromagnetic force, infinities showed up as well. But Richard Feynman, Julian Schwinger, and Shinichiro Tominaga found a technique called renormalization that could absorb these infinities and produce finite, meaningful predictions. Renormalization earned them the Nobel Prize and turned quantum electrodynamics into the most precisely tested theory in all of science. The same renormalization trick was successfully applied to the strong nuclear force and the weak nuclear force. 3 of the 4 fundamental forces of nature were successfully quantized using the framework of quantum field theory plus renormalization. But gravity refused. When you try to renormalize quantum gravity, the infinities multiply. For every infinity you remove, more appear. The theory is, in the technical language of physics, non-renormalizable. The standard techniques that worked so beautifully for the other forces fail completely for gravity. This means that our standard approach to quantum physics simply does not work for gravity. We need something new. We need a completely different framework, a different way of thinking about quantum gravity. And this realization set off a decades-long quest that eventually led to 2 main proposals. One is string theory, which we will discuss later. The other is loop quantum gravity. But before we get to loop quantum gravity, there is one more piece of the crisis we need to understand. Because the incompatibility of general relativity and quantum mechanics is not just an abstract mathematical problem. It has real, physical consequences. There are places in the universe where both theories must be important simultaneously. where gravity is so extreme that quantum effects cannot be ignored, and where quantum mechanics needs gravity to make sense. And at these places, our physics breaks down completely. These places are called singularities. The most famous singularity is the Big Bang. According to general relativity and the standard cosmological model, the universe began approximately 13.8 billion years ago, from a state of infinite density, infinite temperature, and zero volume. All the matter, energy, space, and time in the entire observable universe was compressed into a single point. A singularity. But infinite density is not a physical state. It is a mathematical breakdown. It is the equations saying, I cannot handle this. I am giving you infinity because I do not know what happens here. When a theory predicts infinity for a physical quantity, it means the theory is incomplete. It is telling you that something beyond its scope is happening. At the moment of the Big Bang, the universe was incredibly tiny, incredibly dense, and incredibly hot. Under those conditions, quantum effects of gravity must have been crucial. But general relativity cannot account for quantum effects, and quantum mechanics cannot account for the extreme gravity. Neither theory works. And without a theory of quantum gravity, we literally cannot describe the very beginning of the universe. The other famous singularity is at the center of a black hole. General relativity predicts that when a massive star collapses under its own gravity, it can form a black hole. Inside the black hole, beyond the event horizon, the collapsing matter continues to fall inward until it reaches a point of infinite density, the singularity. Again, infinite density is not physics. It is the theory screaming for help. Inside a black hole, matter is compressed to such extreme densities that quantum gravitational effects must dominate. But we do not have a working theory of quantum gravity. At least not a universally accepted one, so we cannot describe what happens at the center of a black hole. These singularities, the Big Bang and the black hole singularity, are not just embarrassing mathematical glitches. They are telling us something profound. They are telling us that general relativity, despite its extraordinary success, is incomplete. And the way to complete it is to find a quantum theory of gravity. Now, there is a fascinating set of numbers that tells us exactly where quantum gravity becomes important. These are the Planck units, derived in 1899 by the German physicist Max Planck, even before relativity and quantum mechanics were fully developed. If you take the three fundamental constants, the gravitational constant g from gravity, the reduced Planck constant from quantum mechanics, and the speed of light c from relativity, and combine them in specific ways, you get natural units of length, time, and mass. These are the Planck length, the Planck time, and the Planck mass. The Planck length is approximately 1.6 times 10 to the power of negative 35 meters. That is a decimal point followed by 34 zeros and then a 16. It is unimaginably small. Let me try to give you a sense of how small this is. The size of a human hair is about 1/10 of a millimeter, which is 10 to the power of negative 4 meters. An atom is about 10 to the power of negative 10 meters. The nucleus of an atom is about 10 to the power of negative 15 meters. A proton, one of the particles inside the nucleus, is about 10 to the power of negative 15 meters. Now, the smallest thing we have ever directly probed in experiments is about 10 to the power of negative 18 meters, using the Large Hadron Collider at CERN. The Planck length is 10 to the power of negative 35 meters. That is 17 orders of magnitude smaller than the smallest thing we have ever measured. 17 factors of 10. Each factor of 10 means the Planck length is 10 times smaller. 17 of those factors means the Planck length is 100 million billion times smaller than what we can currently probe. Here is another way to think about it. The ratio of the Planck length to the size of a proton is roughly the same as the ratio of the size of a proton to the size of a medium-sized city. That is how far down we are talking about. And here is perhaps the most staggering comparison. If an atom were enlarged to be the size of the entire observable universe, the Planck length at that same scale would still be smaller than an atom. Let that image settle in your mind for a moment. The Planck time is about 5.4 times 10 to the power of negative 44 seconds. This is the time it takes light to travel one Planck length. It is the shortest meaningful interval of time. The Planck mass is about 2.2 times 10 to the power of negative 8 kilograms, roughly the mass of a tiny flea egg. Interestingly, this is large by particle physics standards, far larger than the mass of any known fundamental particle. The Planck energy, which is related to the Planck mass, is about 1 billion electron volts. This is millions of times higher than the energies achieved at the Large Hadron Collider. At the Planck scale, both gravitational and quantum effects are equally important. This is the domain where quantum gravity operates. This is where the smooth spacetime of general relativity is expected to break down and reveal its true, deeper quantum nature. And this is where loop quantum gravity makes its most radical prediction. At the Planck scale, space is not smooth. It is not continuous. It is made of tiny, discrete, indivisible pieces. It is quantized. It has atoms. Atoms of space. But how did physicists arrive at this astonishing idea? To understand that, we need to trace the history. And this history begins with one of the most creative minds in 20th century physics. In 1971, the British mathematician and physicist Roger Penrose published a paper that planted a seed that would take over 2 decades to grow into one of the most important theories in physics. Penrose was thinking about a deep question. In quantum mechanics, one of the most fundamental quantities is angular momentum, the rotational equivalent of straight-line momentum. An angular momentum in quantum mechanics is quantized. It comes in discrete units. Specifically, it comes in multiples of 1/2 of the reduced Planck constant. A particle can have spin 1/2, or spin 1, or spin 3/2, or spin 2, and so on. But it cannot have spin 0.7 or spin 1.3. Only specific discrete values are allowed. Penrose had a bold idea. What if the geometry of space itself could be built entirely from these quantum mechanical spins? What if you could construct space not as a pre-existing background, but as an emergent structure arising from a network of quantum angular momentum relationships? He invented mathematical objects called spin networks. A spin network is a diagram, a graph, made up of nodes which are points, and links which are lines connecting those points. Each link carries a label, a number that represents a quantum spin value, 1/2, 1, 3/2, and so on. Penrose showed that from these simple combinatorial objects, you could recover geometric properties. If you asked the spin network questions about angles and directions, it would give you answers that looked like the answers you would get from ordinary 3-dimensional geometry. At least in an approximate sense when the network is large enough. This was a radical idea. Penrose was suggesting that space is not fundamental, space is derived. Space is an approximation of something deeper, and that something deeper is a quantum combinatorial network described by spin numbers. But in 1971, Penrose's spin networks were an idea without a home. They were beautiful mathematical structures, but there was no physical theory that naturally produced them. They were a solution looking for a problem. And so, for about 15 years, spin networks remained a fascinating but isolated concept, known mainly to a small community of mathematical physicists. The next major breakthrough came in 1986 from a physicist named Abhay Ashtekar, who was working at Syracuse University in the United States. To understand Ashtekar's contribution, you need to know something about the mathematical language of general relativity. Einstein's theory is traditionally written in terms of an object called the metric. The metric is a mathematical tool that tells you how to measure distances and angles in space-time. It encodes the complete geometry, the curvature, the shape, and the dynamics of space-time. Now, when physicists successfully quantized the electromagnetic force, the strong force, and the weak force, they used a mathematical framework based on what are called connections or gauge fields. These are mathematical objects that describe how particles and fields change as you move from one point to another. The quantum theories of these forces, quantum electrodynamics, quantum chromodynamics, and the electroweak theory, are all gauge theories. They are formulated in terms of connections. Here is the problem. General relativity, in its traditional formulation using the metric, does not look like a gauge theory, and all the powerful quantization techniques that worked so brilliantly for the other forces were designed for gauge theories. Trying to quantize gravity using the metric formulation is like trying to fit a square peg into a round hole. Ashtekar's genius was to find a way to rewrite general relativity so that it looks like a gauge theory. He introduced new mathematical variables, now called Ashtekar variables, that describe gravity not in terms of the metric, but in terms of a connection. In this new language, the equations of general relativity take a remarkably simple and elegant form. They look much more like the equations of the gauge theories that describe the other forces. This was a monumental achievement. It did not change the physics of general relativity. The predictions were exactly the same. But it changed the mathematical language, and in physics, the mathematical language matters enormously. It determines which techniques you can apply, which questions you can ask, and which doors you can open. Ashtekar's reformulation opened a door that had been locked for decades. It opened the possibility of applying the powerful quantization techniques of gauge theory to gravity. It was as if someone had translated an ancient, inscrutable text into a language that physicists could finally read. And walking through that door, in 1988, came two young physicists who would change the landscape of theoretical physics. Their names were Carlo Rovelli and Smolin. Rovelli, an Italian physicist who was then at the University of Rome, and Smolin, an American physicist who was then at Yale University, realized something extraordinary. Using Ashtekar's new connection formulation of general relativity, they could find exact solutions to the Wheeler-DeWitt equation. Now, what is the Wheeler-DeWitt equation? It is, in a sense, the Schrödinger equation of the universe. Let me explain. In ordinary quantum mechanics, the Schrödinger equation is the master equation. It tells you how the quantum state of a system, an atom, an electron, whatever, evolves in time. Given the state of the system at one moment, the Schrödinger equation predicts the state at any future moment. In the 1960s, the physicists John Wheeler and Bryce DeWitt tried to write a similar equation for quantum gravity. Instead of describing the quantum state of an atom, this equation would describe the quantum state of the entire geometry of space. The Wheeler-DeWitt equation is, formally, the equation of quantum gravity. It is supposed to describe the quantum behavior of the gravitational field, which is the same as the quantum behavior of spacetime itself. There was just one problem. The Wheeler-DeWitt equation was almost impossibly difficult to solve. In the traditional metric formulation of general relativity, nobody could find exact solutions. The equation was written down, but it just sat there, mocking physicists with its intractability. Rovelli and Smolin discovered that in Ashtekar's connection formulation, the Wheeler-DeWitt equation has exact solutions. And these solutions are loops. Specifically, the solutions are mathematical objects called holonomies, which are integrals of the connection around closed curves, that is, loops in space. This was the birth of loop quantum gravity. The name comes directly from the fact that the quantum states of the gravitational field, the solutions to the fundamental equation of quantum gravity, are described by loops. But Rovelli and Smolin did not stop there. In the years that followed, working with a growing community of physicists, including Jorge Pullin, Jerzy Lewandowski, Thomas Tiemann, and many others, they developed the theory further and made a series of discoveries that would prove to be revolutionary. The most important of these discoveries came in 1994, when Rovelli and Smolin calculated the quantum operators corresponding to area and volume. In any quantum theory, physical quantities are represented by mathematical operators. The eigenvalues of these operators, the values they can take when measured, tell you the possible outcomes of measurements. In ordinary quantum mechanics, the energy operator for a hydrogen atom has discrete eigenvalues, which gives you the discrete energy levels of the atom. This discreteness is the hallmark of quantum mechanics. Rovelli and Smolin calculated the area and volume operators in loop quantum gravity, and they made a stunning discovery. The eigenvalues of the area operator are discrete. The eigenvalues of the volume operator are discrete. This means that area and volume are quantized. They do not take continuous values. They come in specific, discrete chunks. There is a smallest possible non-zero area. There is a smallest possible non-zero volume. Space has a granular structure at the Planck scale. The smallest non-zero area is approximately 10 to the power of negative 66 square centimeters. That is a decimal point, followed by 65 zeros and then a number. Below this area, space simply does not exist, at least not in the way we understand it. It is like asking for a piece of a jigsaw puzzle that is smaller than one piece. You cannot do it. The pieces are the smallest unit. And here is where Penrose's spin networks made their triumphant return. When Rovelli and Smolin examined the mathematical structure of the quantum states of geometry in their theory, they discovered that the basis states, the fundamental building blocks of the quantum geometry, were exactly Penrose's spin networks. The mathematical objects that Penrose had invented in 1971 on purely theoretical grounds turned out to be precisely the objects that naturally emerge when you rigorously quantize general relativity. This was one of those rare and beautiful moments in the history of science when two independent lines of thought developed decades apart for completely different reasons, converge on the same answer. Penrose had dreamed the structure of quantum space 23 years before anyone had the theoretical tools to derive it. Part 2 now, let me describe in detail what these spin networks look like and what they mean. This is the heart of loop quantum gravity, and it is here that the theory makes its most profound and radical claim about the nature of reality. Imagine a vast network, like a three-dimensional web. It has nodes, which you can think of as tiny dots or points, and it has links, lines connecting those dots. The network extends in all directions, with nodes connected to other nodes in an intricate, tangled pattern. Each link in this network carries a label, a number that represents a quantum of angular momentum, a spin. The smallest possible non-zero spin is 1/2. Links can also carry spin 1, spin 3/2, spin 2, and so on, in increments of 1/2. Each node also carries a mathematical label called an intertwiner, which describes how the spins on the links meeting at that node are combined. The intertwiner encodes the detailed quantum geometry at that node. Now, here is the key. In loop quantum gravity, this spin network is space. The nodes of the spin network represent tiny grains of volume. Each node is an atom of space, an indivisible quantum of three-dimensional volume. The volume of each grain is determined by the labels on the links that connect to that node, through a specific mathematical formula. The links of the spin network represent surfaces of area, tiny patches of surface that separate adjacent grains of space. The area of each patch is determined by the spin label on the link, through the area formula I mentioned earlier. So the spin network is a complete description of the quantum geometry of space. It tells you how much volume is in each grain of space, how much area separates adjacent grains, and how all the grains are connected to each other. The entire three-dimensional geometry of a spatial slice of the universe is encoded in a single spin network. Let me use an analogy. Think of a three-dimensional jigsaw puzzle. Each puzzle piece is a tiny chunk of space, a grain of volume. The surfaces where puzzle pieces touch are the areas. The spin network is the blueprint that tells you the size and shape of each piece and how they all fit together. Or think of it this way. You know how a digital photograph is made of pixels. Each pixel is a tiny square of a single color. When you zoom in close enough, you can see the individual pixels. But when you zoom out, the pixels blur together and you see a smooth, continuous image. Loop quantum gravity says that space is like that photograph. At the Planck scale, you would see the individual grains, the nodes and links of the spin network. But at our everyday scale, the grains are so incredibly tiny and so incredibly numerous that they blur together, and space appears perfectly smooth and continuous. How numerous? Let me give you a number that will stagger your imagination. In a single cubic centimeter of space, a volume about the size of a sugar cube, there are approximately 10 to the power of 99 Planck volumes. That is a 1, followed by 99 zeros. Let me put that in perspective. The total number of atoms in the entire observable universe is estimated to be about 10 to the power of 80. So the number of Planck scale grains of space in a single sugar cube is roughly 10 to the power of 19 times larger than the number of atoms in the entire observable universe. That is 10 billion times more grains of space in your sugar cube than atoms in all the stars, planets, gas clouds, and galaxies in the observable cosmos. With that many grains in such a tiny volume, it is no wonder that space looks smooth to us. We would need to zoom in by a factor of 10 to the power of 20 beyond our current experimental capabilities to see the granularity. We are as far from the Planck scale as the Planck scale is from us. It is a double gulf of the unimaginably small. But the mathematical structure of loop quantum gravity tells us that the grains are there. They must be there, because the quantization of area and volume is not an assumption of the theory. It is a prediction. It follows inevitably from the mathematics, just as the quantization of energy levels in a hydrogen atom follows inevitably from the Schrödinger equation. Nobody put the discreteness in by hand. It comes out of the equations on its own. This is one of the most profound aspects of loop quantum gravity. The quantization of space is not something the physicists assumed. They started with Einstein's general relativity, reformulated it using Ashtekar's variables, applied the standard techniques of quantum mechanics, and the discreteness of space popped out of the mathematics like a surprise. Now, there is a concept that is absolutely central to understanding what makes loop quantum gravity special and philosophically deep. It is called background independence. In most of physics, including quantum field theory and string theory, you start by assuming a space-time background. You specify the geometry. You say, for example, that space-time is flat, or that it is curved in a particular way. And then you write equations for particles and fields moving within that pre-specified geometry. The space-time is given in advance. It is the fixed stage on which the physics plays out. But general relativity teaches us that this approach is fundamentally wrong, at least for gravity. In general relativity, the geometry of space-time is not given in advance. It is determined by the matter and energy in the universe. Space tells matter how to move, and matter tells space how to curve. There is no fixed background. The background itself is dynamic. Loop quantum gravity takes this lesson to heart. It is formulated without any reference to a pre-existing space-time. The spin network is not embedded in space. The spin network is space. There is no background. The geometry emerges entirely from the quantum state, from the network of nodes and links and their labels. This is a deep and beautiful idea, but it also makes the theory extremely difficult to work with. In a background-dependent theory, you have a fixed coordinate system, a fixed geometry, a fixed framework within which to do your calculations. In a background-independent theory, you have none of that. You must build the entire framework from scratch, from the quantum state up. Imagine trying to describe the motion of fish in the ocean, but without assuming the ocean exists in advance. Instead, the ocean itself, its shape, its depth, its currents, must emerge from the same equations that describe the fish. That is the challenge of background independence. And loop quantum gravity meets this challenge head-on. The physical meaning of background independence is relational. In loop quantum gravity, the properties of space, distance, area, volume are not properties of some absolute background. They are relationships between the grains of space, between the nodes and links of the spin network. Position is not a property of a point in some pre-existing space. It is a relationship between physical entities. This relational view of space and time goes back to a deep philosophical debate that has been going on for centuries. On one side was Isaac Newton, who believed in absolute space, a fixed, immovable container that exists independently of anything in it. On the other side was Gottfried Wilhelm Leibniz, who argued that space is not a thing in itself, but merely a set of relationships between things. General relativity sided with Leibniz. Space is not a container. It is a network of relationships. And loop quantum gravity makes this precise at the quantum level. The spin network is nothing but a web of relationships, a graph that encodes how grains of space are connected to each other and how much area and volume they carry. Now, so far we have been talking about the structure of space at a single moment, a single snapshot. But the universe is not static. Things change. Space evolves. Stars form and die. Galaxies collide. The universe expands. How does loop quantum gravity describe this evolution? How does it handle time? And here we encounter one of the deepest and most strange aspects of the theory. Because in loop quantum gravity, time as we know it does not exist at the fundamental level. Let me explain this carefully, because it is one of the most counterintuitive and philosophically charged ideas in all of physics. In ordinary quantum mechanics, the Schrödinger equation describes how the quantum state of a system evolves in time. Time is a parameter that appears in the equation. It flows forward. The state changes. Things happen. This is what we all experience, the relentless flow of time. The passage from past to present to future. But in quantum gravity, the situation is radically different. The Wheeler-DeWitt equation, the fundamental equation of quantum gravity, does not contain time. It says that the Hamiltonian operator acting on the quantum state of the universe gives zero. The state does not evolve. Nothing changes. Time is absent. This is called the problem of time in quantum gravity, and it is one of the most debated and most fascinating issues in theoretical physics. How can time not exist when we so obviously experience it? How can the universe be static at its deepest level when everything we see is in constant motion? The answer proposed by loop quantum gravity, and especially by Carlo Rovelli, is that time is not fundamental. Time is emergent. What we experience as the flow of time is a macroscopic, approximate emergent phenomenon that arises from the relationships between physical systems. Think of it this way. Temperature is a real, measurable quantity. You can feel it, measure it, and use it to predict how systems behave. But temperature is not fundamental. At the microscopic level, there is no such thing as temperature. There are just atoms bouncing around. Temperature is a statistical, emergent description of the average behavior of many atoms. It is real, but it is not fundamental. Rovelli suggests that time is similar. At the macroscopic level, time is real and useful. Clocks tick, events happen, causes precede effects. But at the fundamental level, at the Planck scale, there is no time. There are just relationships between quantum grains of space. What we call time is a way of organizing these relationships, a bookkeeping device that emerges when you zoom out and look at the coarse-grained behavior of vast numbers of quantum grains. In Rovelli's own beautiful words, the world is not made of things. It is made of events. And what we call time is simply the way we organize events into sequences. This idea is not universally accepted, of course. Many physicists find it too radical. Some propose alternative solutions to the problem of time. But within the framework of loop quantum gravity, the emergence of time from a fundamentally timeless quantum state is a natural and elegant consequence of the theory's background independence. Now, even though the fundamental theory is timeless, we still need a way to describe how one spin network state transitions to another. We need dynamics. We need to describe the history of quantum spacetime. And this is where spin foams enter the picture. If a spin network is a snapshot of quantum space at one instant, a spin foam is the movie. It is the full spacetime history, the sequence of transitions that takes one spin network state to another. Mathematically, a spin foam is a two-dimensional surface called a two-complex that connects two spin networks. You can think of it as a set of faces, edges, and vertices. The faces carry spin labels, just like the links of spin networks. The edges are where faces meet, and the vertices are special points where the topology of the foam changes, where something happens. Each vertex in a spin foam represents an elementary quantum event, a tiny Planck scale process in which the geometry of space changes. It is the smallest possible event in quantum spacetime. A local rearrangement of the spin network where links are created, destroyed, or reconnected. The amplitude, the quantum mechanical probability, associated with each spin foam configuration, tells you how likely that particular space-time history is. To compute the total probability of going from one spin network state to another, you must sum over all possible spin foam histories that connect them. This is the quantum gravity version of Feynman's path integral, the sum over histories that is the foundation of quantum field theory. The spin foam approach to loop quantum gravity was proposed by Michael Reisenberger and Carlo Rovelli in 1997. The first detailed model was the Barrett-Crane model, proposed by John Barrett and Louis Crane. But the model that is currently considered the state-of-the-art is the April model, named after Jonathan Engel, Roberto Pereira, Carlo Rovelli, and Ettore Levine, who developed it in 2008. The April model has several remarkable properties. First, it has been shown to have the correct classical limit. This means that when you zoom out, when you look at the large-scale, coarse-grained behavior of the spin foam, you recover Einstein's general relativity. The smooth, continuous space-time of GR emerges as an approximation of the discrete quantum spin foam geometry. Second, the amplitudes in the April model are finite. This is a crucial result. Remember, the whole problem with trying to quantize gravity using traditional methods was that the calculations produced infinities. In the spin foam formulation of loop quantum gravity, these infinities do not appear. The theory is finite. The ultraviolet divergences, the infinities that plague conventional quantum gravity, are automatically cured by the discreteness of space at the Planck scale. The grains of space act as a natural cutoff, preventing the infinities that would arise if space were truly continuous. This finiteness is one of the strongest arguments in favor of loop quantum gravity. It suggests that the discreteness of space is not just a mathematical curiosity, but a physical necessity, a feature that nature may actually use to keep quantum gravity well-defined and consistent. The spin foam approach also provides a beautiful bridge between loop quantum gravity and other areas of physics. Spin foams are mathematically related to topological quantum field theories, to lattice gauge theories, and to various models in statistical mechanics. These connections open up a rich mathematical landscape and suggest that loop quantum gravity is part of a larger, deeper mathematical structure. Now, let us make a brief pause here. We have covered a lot of ground. We have seen the crisis that motivated loop quantum gravity, the history of how the theory was developed, the structure of spin networks and spin foams, the quantization of area and volume, background independence, and the emergence of time. But so far, our discussion has been largely abstract. What does loop quantum gravity predict about the actual universe? What does it say about specific physical situations? And this is where the theory truly shines. Because loop quantum gravity has been applied to two of the most extreme and fascinating situations in the universe: the Big Bang and black holes. And in both cases, the results are nothing short of revolutionary. Let us start with the Big Bang, or, as loop quantum gravity suggests we should call it, the Big Bounce. As we discussed earlier, standard cosmology based on general relativity tells us that the universe began with a singularity, a point of infinite density approximately 13.8 billion years ago. If we run the expansion of the universe backward in time, all the matter and energy in the cosmos comes together, the density increases, the temperature rises, and eventually, at time zero, everything is compressed into a single point. Density becomes infinite, temperature becomes infinite, the volume of the universe becomes zero, the curvature of space-time becomes infinite. Physics breaks down. This is the Big Bang singularity. And it is not just an inconvenience, it is a fundamental barrier to our understanding. We cannot ask what happened before the Big Bang, because in general relativity, there is no before. Time itself begins at the singularity. It is like asking what is south of the South Pole. The question does not make sense within the framework of the theory. But what if the framework is wrong? What if the Big Bang singularity is not a real physical event, but an artifact of using the wrong theory? Of pushing general relativity beyond its domain of validity? This is exactly what loop quantum gravity suggests. In the early 2000s, a physicist named Martin Bogerwald applied the techniques of loop quantum gravity to a simplified cosmological model, a homogeneous isotropic universe, the kind described by the standard Friedmann equations of cosmology. He found something remarkable. When you quantize this cosmological model using LQG techniques, the Big Bang singularity disappears. It is replaced by a quantum bounce. This line of research was then made mathematically rigorous and physically detailed by Abhay Ashtekar, Tomasz Pawlowski, and Parampreet Singh in a series of landmark papers published around 2006. They developed what is now called loop quantum cosmology, or LQC, the application of loop quantum gravity to the study of the early universe. Here is what loop quantum cosmology tells us. As we run the universe backward in time, the density increases, just as in classical cosmology. But as the density approaches the Planck density, approximately 10 to the power of 93 grams per cubic centimeter, something new happens. The quantum nature of space kicks in. The discrete granular structure of space at the Planck scale creates an effective repulsive force, a quantum gravitational repulsion that opposes further contraction. This repulsive force is not put in by hand. It is not an assumption. It emerges naturally from the quantum geometry of LQG. It arises because the discrete quanta of area and volume resist being compressed below their minimum size. Space literally pushes back against being crushed. As the universe continues to contract, the quantum repulsive force grows stronger and stronger until it exactly balances and then overwhelms the attractive force of gravity. At this point, the contraction stops and the universe begins to expand again. It bounces. The maximum density reached at the bounce point is approximately 41% of the Planck density. This is enormous. About 10 to the power of 93 grams per cubic centimeter, but it is finite. It is not infinite. The singularity is gone. Let me use an analogy that might help. Imagine a ball falling toward the ground. In classical physics, if the ground is perfectly rigid and infinitely thin, the ball hits the ground and stops, the singularity. But what if the ground is actually a trampoline? The ball falls, hits the trampoline, and bounces back up. The harder the ball falls, the harder the trampoline pushes back, until the ball reverses direction and begins to rise. Loop quantum cosmology turns the Big Bang singularity into a quantum trampoline. The universe falls, reaches the trampoline at the Planck density, and bounces. The Big Bang was not the beginning, it was the moment of the bounce. And this has a staggering implication. There was a universe before ours. Before the bounce, there was a contracting universe. A universe that may have looked much like ours, with galaxies and stars and planets, but which was in a phase of contraction rather than expansion. That universe contracted, its density increased, quantum gravity effects kicked in, the contraction stopped, the universe bounced, and the expansion phase began. Our Big Bang was the bounce. Our expanding universe is the aftermath. Is this the same universe recycling, contracting and expanding over and over in an eternal cycle? Or is it a one-time event, with one contraction phase followed by one bounce, followed by one expansion? Loop quantum cosmology does not definitively answer this question yet. The simplest models show a single bounce, but more complex models could allow for multiple bounces. What we do know is that the quantum bounce is robust. It occurs in all the models that have been studied within loop quantum cosmology, regardless of the specific details. Different types of matter, different initial conditions, different assumptions about the shape of the universe, all lead to the same qualitative result. The singularity is replaced by a bounce. This robustness gives physicists confidence that the bounce is a genuine prediction of the theory, not an artifact of simplifying assumptions. But can we test this? Can we find evidence for the big bounce? The most promising avenue is the cosmic microwave background, or CMB, the faint glow of radiation left over from the hot, dense early universe, about 380,000 years after the Big Bang. The CMB is the oldest light in the universe, and it carries an imprint of the conditions in the very early cosmos. Loop quantum cosmology makes specific predictions about the CMB. Because the quantum bounce is slightly different from the classical Big Bang singularity, the primordial fluctuations, the tiny variations in density that eventually grew into galaxies, and the large-scale structure of the universe should be subtly different from what standard classical cosmology predicts. In particular, LQC predicts modifications to the power spectrum of the CMB at the largest angular scales. These are the largest patterns in the CMB, corresponding to the lowest multipoles. Standard cosmology based on inflation predicts specific values for these largest scale fluctuations, and the actual observations from the Planck satellite show some interesting anomalies at these scales. The observed power at the largest scales is lower than what standard inflation predicts. Some researchers have suggested that this could be a hint of loop quantum cosmology effects. But the evidence is not conclusive. The anomalies could also be statistical flukes or could have other explanations. In 2020, a detailed study by Abhay Ashtekar and colleagues computed the specific predictions of LQC for the CMB and compared them with Planck satellite data. The results were intriguing. Several of the observed large-scale anomalies were naturally explained by LQC effects, but the statistical significance was not high enough to claim a detection. More precise future observations, such as those from next-generation CMB experiments, might be able to distinguish between the predictions of LQC and standard inflation. It is worth emphasizing that even if we cannot definitively confirm the Big Bounce with current data, the mere existence of a mathematically rigorous, physically motivated theory in which the Big Bang singularity is resolved is a major achievement. For the first time in history, we have a framework that allows us to describe the very beginning of the universe without the physics breaking down. Now let us turn to the other great singularity in physics, the one hiding inside every black hole. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own gravity. If the star is massive enough, no known force can halt the collapse. The star implodes. The outer layers may be blown off in a supernova explosion, but the core collapses inward, passing through the event horizon and forming a black hole. According to general relativity, the collapse continues inexorably. The matter falls inward, the density increases, the curvature of space-time grows, and eventually everything reaches a single point of infinite density, the singularity. This singularity sits at the center of the black hole, hidden behind the event horizon. where the curvature of space-time is so extreme that nothing, not even light, can escape. But just as the Big Bang singularity is a sign that general relativity is incomplete, the black hole singularity is also a sign that general relativity is incomplete. At the extreme densities inside a black hole, quantum gravitational effects must be important. And just as loop quantum gravity replaces the Big Bang singularity with a bounce, it is expected to replace the black hole singularity with something finite and well-defined. The picture that emerges from applying LQG techniques to black hole interiors is fascinating. As the collapsing matter approaches Planck density, the quantum repulsive force kicks in, just as it does in the cosmological case. The collapse stops. The matter does not crush to a point of infinite density. Instead, it reaches a maximum finite density and then begins to expand again. This leads to the concept of a Planck star, proposed by Carlo Rovelli and Francesca Vidotto. A Planck star is a hypothetical object that forms when the collapsing matter inside a black hole reaches Planck density and bounces. From the inside, the bounce happens relatively quickly, but from the outside, due to the extreme time dilation near the event horizon, the bounce takes an extraordinarily long time, potentially longer than the current age of the universe. So from our perspective, looking at a black hole from the outside, the Planck star looks just like a regular black hole. It is hidden behind the event horizon. But from the perspective of the matter inside, the singularity never forms. The collapse reverses, and the matter begins to expand. What happens next is one of the most speculative but intriguing predictions of the theory. Some researchers, including Rovelli and Vidotto, have proposed that eventually, after an extremely long time, the black hole transitions into a white hole. A white hole is the time reverse of a black hole. Instead of being a region that nothing can escape from, a white hole is a region that nothing can enter. It only expels matter and radiation. In this picture, the complete life cycle of a collapsed star is collapse, bounce at Planck density, and eventual emergence as a white hole. The matter that fell into the black hole eventually comes back out. This process takes an enormously long time as seen from the outside, but it is finite. This idea is still highly speculative and is the subject of active research, but it offers a tantalizing resolution to one of the most profound puzzles in physics: the black hole information paradox. The information paradox was first identified by Stephen Hawking in 1974. Hawking showed that black holes are not truly black. They emit a faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly lose mass and shrink over time. If you wait long enough, the black hole will evaporate completely. But here is the problem. The Hawking radiation is thermal. It carries no information about what fell into the black hole. It is like the heat radiating from a burning book. The book might have contained a novel or a phone directory, but the heat you feel tells you nothing about the content. All the information is lost. If the black hole evaporates completely, all the information about everything that ever fell in. Every atom of every star, every bit of every physical process is destroyed, gone forever. But this violates a fundamental principle of quantum mechanics called unitarity, which says that information is never truly lost. It can be scrambled, it can be hidden, but it must be preserved somewhere. This is the information paradox. Hawking radiation says information is lost. Quantum mechanics says information cannot be lost. They cannot both be right. Loop quantum gravity offers a possible resolution. If the black hole does not evaporate completely, but instead bounces into a white hole, the information is not lost. It comes back out through the white hole. The bounce at Planck density preserves the quantum information, because the evolution through the bounce is unitary. Nothing is destroyed. The information is merely hidden for a very long time and then released. This is not a proven solution to the information paradox. It is a proposal, a possibility suggested by the framework of loop quantum gravity. But it is a remarkably elegant one, and it demonstrates the power of the theory to address some of the deepest problems in physics. There is another major success of loop quantum gravity regarding black holes, and it is more established and less speculative. It is the derivation of black hole entropy. In 1972, Jacob Bekenstein proposed, based on theoretical arguments, that black holes have entropy. Entropy is a measure of disorder, or more precisely, a measure of the number of microscopic states that are consistent with the macroscopic properties of a system. A gas in a box, for example, has many possible arrangements of its atoms that all look the same macroscopically, same temperature, same pressure. Each arrangement is a microstate. The entropy counts the number of microstates. Bekenstein argued that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was surprising, because for ordinary systems, entropy is proportional to volume. The fact that black hole entropy scales with area was one of the first hints of what is now called the holographic principle, the idea that the information content of a region of space can be encoded on its boundary. Hawking later made Bekenstein's proposal precise by deriving the exact formula: the entropy of a black hole equals 1/4 of the area of its event horizon, measured in Planck units. This is the Bekenstein-Hawking entropy formula, and it is one of the most important equations in theoretical physics. But there was a mystery. If black hole entropy counts microstates, what are those microstates? What is the microscopic structure that gives rise to the entropy? Bekenstein and Hawking derived the formula using semi-classical arguments, a combination of general relativity and quantum field theory. They did not identify the microstates. It was as if someone had counted the number of ways to arrange something without knowing what was being arranged. Loop quantum gravity provides an answer. In LQG, the horizon of a black hole is a surface, and like all surfaces in LQG, it is made up of tiny patches of quantized area. Each patch corresponds to a link of the spin network, puncturing the horizon. Each such puncture carries a spin label, and different assignments of spin labels to the punctures give different microstates. The entropy of the black hole comes from counting the number of different ways the spin network can puncture the horizon while producing the correct total area. This is a well-defined combinatorial problem, and when you solve it, you get an answer that is proportional to the area of the horizon, exactly as Bekenstein and Hawking predicted. However, to get the exact coefficient, 1/4, you need to fix the Emirci parameter. The Emirci parameter, named after the Italian physicist Giorgio Emirci, is a free parameter in loop quantum gravity that appears in the formula for the area eigenvalues. It is analogous to a coupling constant in other theories. By requiring the LCEG calculation of black hole entropy to match the Bekenstein-Hawking formula, the Emirci parameter is fixed to approximately 0.274. Some physicists view this as a weakness. The Emirci parameter is fixed by matching an already known result rather than being predicted independently. Others view it as a strength, the fact that LQG can reproduce the correct black hole entropy at all, from a microscopic counting of quantum gravitational states is a highly non-trivial achievement. It provides a concrete, physical interpretation of black hole entropy in terms of the quantum structure of space at the horizon. The black hole entropy calculation is considered one of the landmark results of loop quantum gravity. Together with the resolution of the Big Bang singularity, it demonstrates that the theory is not just a mathematical framework, but a physically meaningful theory that can make contact with known results and provide new insights into the most extreme phenomena in the universe. Now, I want to take a moment to address something that might be on your mind. You might be wondering, if loop quantum gravity is so powerful, why is it not universally accepted? Why is there still a rival theory, string theory, and what are the differences between them? The rivalry between loop quantum gravity and string theory is one of the great intellectual dramas of modern physics. It has been going on for decades, and it touches on deep questions about not just the structure of reality, but also the methodology and philosophy of science. Let me describe both sides fairly. String theory emerged in the late 1960s and early 1970s, originally as an attempt to describe the strong nuclear force. It was then recognized in the mid-1980s as a potential theory of quantum gravity, and it has since become the dominant approach to quantum gravity in terms of the number of researchers working on it and the institutional support it receives. The basic idea of string theory is this: the fundamental building blocks of nature are not point-like particles, but tiny, one-dimensional objects called strings. These strings can vibrate in different patterns, just like a guitar string can vibrate to produce different notes. Each vibration pattern corresponds to a different particle. One vibration pattern gives you an electron, another gives you a quark, another gives you a photon, and crucially, one vibration pattern gives you a graviton, the hypothetical quantum of the gravitational field. This is one of string theory's greatest selling points. It naturally incorporates gravity. The graviton emerges automatically as one of the vibration modes of the string. You do not need to add gravity by hand. It comes for free. But string theory comes with some heavy mathematical baggage. The equations of string theory are only consistent in a specific number of space-time dimensions, 10 for superstring theory or 11 for the more general M-theory framework. Our universe, as far as we can tell, has only 4 space-time dimensions, 3 of space and 1 of time. So where are the extra 6 or 7 dimensions? String theorists propose that the extra dimensions are compactified, curled up into incredibly tiny shapes so small that we cannot detect them. These tiny shapes are called Calabi-Yau manifolds, and they come in an enormous number of possible configurations. In fact, the number of possible compactifications, the number of ways the extra dimensions can be curled up, is estimated to be around 10 to the power of 500. This vast collection of possibilities is called the string theory landscape. The landscape is both a strength and a weakness. On one hand, it means string theory is incredibly rich, with a vast mathematical structure. On the other hand, it means the theory does not make a unique prediction about the low-energy physics of our universe. There are 10 to the power of 500 possible versions of string theory, and it is not clear which one, if any, describes the universe we live in. Some critics argue that a theory that can accommodate virtually anything predicts essentially nothing. String theory is also background dependent, at least in its current formulation. The strings vibrate in a pre-existing spacetime background. The geometry of spacetime is given in advance, and the theory describes the behavior of strings within that geometry. There have been important efforts to make string theory background independent, notably through the holographic principle and the anti-de Sitter conformal field theory correspondence. But the theory is not yet fully background independent in the way that loop quantum gravity is. String theory is also more ambitious than loop quantum gravity. It aims to be a theory of everything, a single framework that unifies all four fundamental forces: gravity, electromagnetism, the strong force, and the weak force, and all the fundamental particles. LQG, by contrast, is a theory of quantum gravity alone. It does not claim to unify gravity with the other forces. Now, let me describe how loop quantum gravity differs from string theory, fairly and clearly. The first difference is dimensionality. Loop quantum gravity works in exactly 4 spacetime dimensions, the 4 dimensions we observe. It does not require any extra dimensions. There are no compactified spaces, no Calabi-Yau manifolds, no landscape of 10 to the power of 500 possibilities. The second difference is background independence. Loop quantum gravity is background independent from the ground up. There is no pre-existing space-time. The geometry of space and time emerges from the quantum state. This is a direct implementation of Einstein's deepest insight in general relativity, that space-time is dynamical, not fixed. The third difference is the introduction of new entities. String theory introduces fundamentally new objects, strings, branes, and extra dimensions that do not appear in our current theories. Loop quantum gravity introduces no new objects. It takes the existing theory, general relativity, and quantizes it using standard quantum mechanical methods. The spin networks and spin foams are not new entities added to the theory. They are the quantum states and histories that emerge naturally from quantizing the gravitational field. The fourth difference is scope. String theory aims to explain everything, all forces and all particles. LQG focuses specifically on gravity. This makes string theory more ambitious, but it also means string theory must account for a much wider range of phenomena. LQG's more modest scope allows it to make more focused, concrete progress on the problem of quantum gravity. The fifth difference is mathematical rigor. Loop quantum gravity is generally considered more mathematically rigorous than string theory, in the sense that many of its foundational results, the quantization of area and volume, the finiteness of spin foam amplitudes, the resolution of singularities in loop quantum cosmology, have been proven rigorously. String theory, while spectacularly rich mathematically, is less rigorous in some of its foundational aspects, particularly regarding the non-perturbative formulation of the theory. On the other hand, string theory has produced a wealth of results in pure mathematics in areas like algebraic geometry, topology, and number theory. It has also provided deep insights into the nature of quantum gravity through the holographic principle and the study of black hole entropy in specific string theory models. String theory's calculation of black hole entropy for certain classes of black holes, known as extremal black holes, reproduces the Bekenstein-Hawking formula exactly, including the correct numerical coefficient without any adjustable parameters. This is a remarkable achievement. So which theory is right? This is the million-dollar question, and the honest answer is, we do not know. Both theories have significant achievements. Both face significant challenges, and it is entirely possible that both are partially right. That the true theory of quantum gravity incorporates elements of both. In fact, there have been some fascinating hints of convergence. In certain simplified models, results from loop quantum gravity and string theory agree. Some researchers have found mathematical connections between spin foams and certain string theory amplitudes. The holographic principle which emerged from string theory, may also play a role in loop quantum gravity. The physicist Lee Smolin, one of the founders of loop quantum gravity, has proposed that the two theories might be different descriptions of the same underlying reality, different windows looking into the same room. Others are more skeptical, seeing the two approaches as fundamentally incompatible. What is clear is that the problem of quantum gravity is one of the most difficult and most important problems in all of science, and having multiple approaches to it is a good thing. Science progresses through competition and critique. The tension between loop quantum gravity and string theory has pushed both fields forward and forced both communities to address their weaknesses and sharpen their arguments. Now, let us address a question that many people ask about any physical theory. Can we test it? Can we do experiments that would confirm or falsify loop quantum gravity?